All right, good morning. So, you may have noticed there's a technical problem. The Blackboard is not being projected yet, but that's okay because I'm just going to yak for maybe 10 minutes. And then I'll start writing things on the board, and by then, maybe it will be projected. So first, let me remind you very rapidly of the rules of the game. Please ask questions, interrupt me. I'm going to start going a lot faster because I'm hoping to get to the fun stuff today and tomorrow. And if I don't go faster, I won't get there. So the only way to slow me down is if you start asking lots of questions. You've been asking questions. They've all been great. Keep that up. I will lecture through the 10-minute question period at the end, so get your questions in when you can. Let me remind you of what we did yesterday. We have actually reached one of the profound conclusions I mentioned in my first lecture about what happens when you try to combine relativity and quantum mechanics. The first thing we discovered is that we've been doing it wrong all our lives. In quantum mechanics, where we localize particles, that is, the states are localized in space, is completely wrong. That's not the way the world works. It's the observations that are localized, not the objects we observe. We reached that conclusion by starting with some very simple principles: causality, E equals mc squared, and basic quantum mechanics, and we're led more or less inexorably to the enlargement of the Hilbert space to include multi-particle states, particle production, and the like. And from there, with some rather modest assumptions, we discovered local observables. So we got to the Fock space, which we described all of the observables using creation and annihilation operators. Remember these raising and lowering operators for each momentum that a particle might have. And then discovered somewhat miraculously that with a small number of assumptions, all of which I can justify for you in great detail if we had a year-long course, and we ended up with the simple observation that everything we did, every line, could be obtained by working in a totally different direction, by starting with a classical theory of fields, where the degrees of freedom of a mechanical system are actually objects that carry a space-time label, and then we just do canonical quantization, something that would have been familiar to the early quantum mechanics pioneers of the 1920s and 30s, and somehow we are magically going to arrive at the same conclusion: the Fock space, creation annihilation operators, and local observables. So the nice thing about this observation and why it's so important is that it's very laborious and annoying to have to start always with the creation annihilation operators and work our way up to the quantum fields, especially when we start talking about the interactions among particles. Much easier to start with the classical field theory and quantize it, knowing that at the end of the day, those creation annihilation operators and the particles and local observables and all of that is going to drop out. And today we will see why that is such an efficient way of talking about things. Okay, so I'm going to pause here just for a moment in the vain hope that when I turn around, my Blackboard will be projected on the screen. Oh well. And pause and ask if there are any questions about what we did last time before we get going today. Nope, no questions. Okay, great. Today, we actually begin to reap the rewards of the orgy of mathematics that we went through yesterday. So we're going to, in fact, start by solving a very simple problem that most of you have seen solved before, and even if you haven't seen it, you probably know the solution. I'm going to ask a simple question that every physicist has asked at one point in their lives. Why is the sky blue? You all know the answer? Yeah. So why am I asking that question in this venue? Here we are at a laboratory investing short distance, and I ask you a classical question from solved in the late 19th century, having nothing to do, in fact, at the time of its solution, with either quantum mechanics or relativity or anything related to this. Well, there's a good reason for it. First of all, because it's interesting. It's always fun to do interesting things, even if it might be a textbook exercise by now. But more importantly, it is the simplest example I could think of that demonstrates the power of this approach. It's also in a context with which you are very familiar. It's non-relativistic, so we don't have to think about all the complications of relativity, even though we got to this point by starting with relativity. Nevertheless, we can use this to discuss things even in the non-relativistic limit. After all, the non-relativistic limit is a limit of a relativistic system. It should still be true.
Could you remind me, what do you have to mention there? He doesn't know what to do.
Oh, he's supposed to use the camera to project what is on the Blackboard up on the screen. what was I saying? Something. Oh yes, non-relativistic. So non-relativistic is just fine because it is the limit of a relativistic system. It is also something that you are very familiar with, and it will avoid some of the complications that will arise when we start approaching relativistic systems. So let me start a little bit with the why the sky is blue. As you all mentioned to me, it was answered correctly by a physicist from the late 19th century, Lord Rayleigh. It had actually been answered incorrectly by a variety of physicists before him, although they were on the right track. What Rayleigh did was he investigated the classical scattering of electromagnetic waves off of little dielectric spheres. Right? He didn't know about quantum mechanics. He didn't really know about atoms and things like that. But he assumed that the atmosphere, the gas, was made of tiny little particles, and he treated them as little dielectric spheres, and then he just did classical E&M the way you've done it in undergraduate or graduate courses in electricity and magnetism. That is not a fun calculation. It is a textbook or possibly a homework exercise in a graduate E&M course to figure out what the scattering of light does by dielectric spheres, but we're going to get essentially his entire answer in 3 lines. Okay, no work. However, to get to the point where we can do it in 3 lines is going to take most of today. So, as always, it's what you know and then what you can do with it. The first thing we're going to do is simplify our formalism a little bit with the observation that we're dealing with a non-relativistic system. Consequently, even though we're using our fields to do everything, we no longer have to worry about particle creation. Right? That was a consequence of E equals mc squared. We don't have E equals mc squared, so we can just treat a definite number of particles in our Hilbert space, the incoming photon, the incoming molecule of air that the light is going to scatter off, the outgoing light, the outgoing molecule. I don't need to consider in my Hilbert space. Yes, that's perfect. Thank you very much. Multiple molecules. Notice that the field that we have constructed contains a part for the creation of particles and a part for the annihilation of particles, and we argued last time that both of those pieces being present was essential for relativistic causality. You remember that we said that observables had to be local, so if we consider 2 separate observables, one here and one at a space-like separated point, they can't interfere with each other in any way. Therefore, in quantum mechanics, they have to commute. That commutation required both of these pieces to be present. And it's why we couldn't take a field that was some other linear combination of an A and A dagger, like A minus A dagger. But in the non-relativistic limit, there's no problem with that. There's no particle creation to worry about. There's no maximal speed, so causality is not an issue. So in fact, we can break phi up into 2 pieces, the creation part and the annihilation part, and deal with them separately. Okay, we won't be able to do that in the relativistic case, but in a non-relativistic case we can, and it makes life much easier. And are non-relativistic. Okay, so that's going to simplify our lives. But how are we going to get started with this? Well, the first thing we need to do is figure out what fields we need. Remember, the fields correspond to particles. That's what's going to come out of this canonical quantization. So we just have to figure out what particles we're dealing with. Well, we're dealing with light, so we need the field appropriate for creating and annihilating the light. That's the electromagnetic field. So that one's easy. Well, what else do we have? Well, of course, the air that we're considering the scattering of light by is composed mostly of nitrogen. In fact, it's nitrogen molecules. A typical nitrogen atom likes to bond with another nitrogen atom, making N2, a nitrogen molecule. That accounts for about 70% of the molecules of air, so we might as well just consider the scattering off of those nitrogen molecules. Well, but the nitrogen molecule is a bound state of 2 nitrogen atoms, so presumably I need a field to create and annihilate the nitrogen atom, and then I'll figure out how they combine to make the nitrogen molecule. But wait, that nitrogen atom is itself a composite of electrons and a nucleus. So I guess I'm going to need a field that creates the electron and a field that creates the nucleus and figure out how they all get bound together into that atom. But wait, that nucleus is a composite of protons and neutrons. So I guess really I need a field that creates and annihilates protons and neutrons, one for the proton, one for the neutron, and then I'll have to include whatever combines the protons and neutrons into a nucleus. But wait, those protons and neutrons are composites of quarks and gluons. So I guess I'm going to need a field really of quarks and gluons and an interaction which binds all of those up into the hadrons, the protons and neutrons, etc. But wait, the quarks are composites of, well, we don't know. Maybe they're composites of something else. In fact, that's one of the things that this laboratory is doing right now, is trying to see whether quarks are indeed composite objects from some underlying structure. But you see that we have arrived at what would be a total disaster if it's true. Well, depending on your point of view. If I don't know what quarks are made of, I can't continue in this way. I'm now stuck. I can't start trying to write down the appropriate fields necessary to calculate my scattering of light by air molecules without knowing what happens at arbitrarily short distances. Well, fortunately, or unfortunately, depending on your point of view, that's not how the world works. When you in elementary quantum mechanics figured out the energy levels of hydrogen, you know, that minus 13.6 electron volts with the 1 over n squared, you took a point-like nucleus, in this case a proton, and an electron, and you solved the quantum mechanics of that problem. You didn't worry about the substructure of the proton. You didn't worry that the proton was a composite of quarks. You didn't worry that the quarks might themselves be composites of something else. So why not? Why didn't you worry about it?
The distance scale.
It's the distance scale. So can you be more quantitative?
So compared to the interaction with the strong force, that it would have fallen off exponentially compared to where the electron was, so it wouldn't have an effect. So I mean,
Okay, so let me interrupt you. So basically right, except you don't even need to be talking about the strong force and falling off exponentially and all of that. By the way, that would presuppose that I know something about the interaction that might bind the quarks. I have to say it falls off. Okay, that would be also not great if I have to make comments like that. But you're on the right track. How big is the nucleus? A proton? Yeah, 10 to the minus 15 meters or so. And in an atom, where do we find the electron? Right, it's got a wave function. That wave function is spread out over some region. How big is the region over which the electron is spread out? 10 inches. What? Meters. 10 to the minus 10 meters. That's about right. So the nuclear size is about 10 to the minus 15 meters, whereas the atomic size set by the electron is the Bohr radius, approximately, which is about a half 10 to the minus 10 meters. That is, it's 50,000 times larger. So that electron is spread out over this very large region, and throughout the vast majority of that volume, there's no proton to worry about. The proton really is this point-like object just at the center, and in fact what happens is that the electron is really only sensitive to averages over regions of space that are much larger than the region occupied by the proton. In fact, this averaging over things means that whatever substructure is inside that proton, the electron is totally insensitive to it. If I draw a picture of the 3 quarks in the proton, and you don't look at the screen, I guarantee you no one in the back of the room knows that there are 3 quarks in my proton. So it's this averaging that that makes everything work. And as we'll see probably next time, there's a technical treatment of this averaging which led to a Nobel Prize about 2 decades ago. So as simple as this sounds, it's absolutely essential that if we're making measurements that average over large distances, then what's happening at short distances should be mostly irrelevant, or at least the details of what's happening should be mostly irrelevant. Our goal today and tomorrow is to actually make that precise, which is why we're starting with this. Yeah, question?
Excuse me, could the screen be zoomed a little bit again?
I don't know, is anyone in there?
Somebody was tinkering with it.
Someone was just tinkering with it. Well, if anyone is listening, yeah, I see someone going, no. If anyone is in there, zoom the screen. If not, what can we do? All right. Is Diego still here? Okay, sorry about that. Technical problems. Okay, so before we proceed with our discussion of the scattering of light by molecules, we started by saying, what are the right fields to include, the right degrees of freedom? In order to answer that question properly, we have to ask what length scales are relevant. Surely the length scales associated with any substructure of quarks is not going to be relevant, but let's be careful. So for the sky is blue, we're interested in the scattering of visible light. So we know the wavelength of the light by air molecules, whose size we also know. So let's start with the wavelength of visible light. What's the wavelength of visible light?
100 nanometers.
Yeah. So the wavelength of visible light is on the order of 10 to the minus 7 meters or so. And the molecule size is set by the Bohr radius, which, since it's a molecule, it's somewhat larger than the hydrogen, but not that much larger. So this is much, much greater than the Bohr radius. And so our first observation is because the probe that we're using, this wavelength of light, is so long compared to the size of the molecule that no substructure of the molecule can possibly be relevant. We average over it. So now we're back where you probably would have started without having had this conversation. The only field we need to worry about is the one that creates and annihilates the molecule. So I don't need a field for the electron. I don't need a field for the nucleus. I don't even need a field for the nitrogen atom separately because the distance between the two nitrogen atoms and the molecule is small compared to that 10 to the minus 7 meters. Okay, so I'm going to introduce a field F and a field F dagger. One of them contains the annihilation part, namely the F, and one contains the creation part, F dagger, for the molecule. As we've already said, so F and F dagger for the molecule, and the electric and magnetic fields to create and annihilate the light. Okay, so now in order to proceed, remember our strategy is to use the fact that the canonical quantization of a classical mechanical system will give us what we want. So I'm going to write down the Hamiltonian, the energy of our combined system, light plus molecules. So to do that, we're going to write it in pieces. First, I want the energy associated with the molecules. Well, they're non-relativistic, so I don't need to worry about the mass energy. That's just a constant, and an overall constant in the energy never matters. It's only differences of energies that matter, so I can forget about that. So for the molecule, its energy is just its kinetic energy, p squared over 2m, where m is the mass of the molecule. So I can easily write down that Hamiltonian. So I've written it using the creation annihilation operators. That's just to help keep you oriented. Now I'm going to go back and write it in terms of the field. Okay, this should not be too surprising even if you can't see it in your head immediately. Remember the field F was then e to the minus ik dot x, sorry, e to the minus ip dot x a of p integrated over p. So the derivative with respect to x pulls down a p, so the two derivatives in the integral d cubed x there is the p squared over 2m. The integral d cubed x over all space guarantees that the momentum in the F and the momentum in the F dagger match together, and then you're left just with A dagger A. Okay. In fact, that's the next homework problem, is just to verify that that's true. Okay. It's very simple. If you're having trouble with it, let me know and I'll help you. Okay, before we proceed, let's ask what the dimension of F is. You remember we spent a little bit of time early on in these lectures with this fancy notation of the square brackets to talk about the mass dimension of things. So let's try to figure out what the mass dimension of F is. Well, the mass dimension of H is 1. It's an energy. The mass dimension of, well, I have 3 spatial dimensions upstairs, and I have 2 derivatives. A derivative, d by dx, is a spatial dimension downstairs. So that's 3 spatial dimensions upstairs, 2 downstairs. That leaves you 1 upstairs. 1 spatial dimension upstairs is like 1 mass dimension downstairs. So that's a minus 1. I have another mass downstairs that's minus 2. Right? Minus 2, and the whole thing is supposed to equal 1. So you get the dimension of this tells you that the dimension of F squared should be 3, or the dimension of F is 3/2. Mass dimension 3/2. Okay, did you get that? You want me to do it again? Okay, 3/2. That will be key to everything that happens again. What about the photons? So this was my nitrogen Hamiltonian. What about the photons? Well, I need the energy associated with the photons. Well, you all know that from basic E&M. The energy density in the electromagnetic field is just E squared plus B squared over 4 pi or 8 pi or something like that. So to get the total energy, the Hamiltonian, you integrate that over all of space. So I'm going to do the same thing. I'm going to ask what is the dimension of the electric field and the magnetic field. Notice they have the same dimension. Well, traditionally you probably didn't think of the electric and magnetic fields as having the same dimensions. You don't usually measure them with the same unit. But when you take the speed of light to be 1, they come out with the same unit. So the dimension of E is equal to the dimension of B. And by looking at this, it's 2. Again, the integral of E squared must have mass dimension 1. The d cubed x is mass dimension minus 3. So E squared has to have mass dimension 4. E is half of that, dimension 2. Okay, everybody happy? And now we are almost done. We have our Hamiltonian for the molecule. We have our Hamiltonian for the photons, for the light, excuse me, but we need an interaction between them. And now you should all be looking nervous. Well, you know what that interaction looks like. You have to write down the Maxwell equations with the current on one side, and then you have to write down the Lorentz force law on the charges, and but the charges are inside the nitrogen molecule, so maybe it's a dipole or something, and we're going to have to spend the rest of our time at CERN, the next 6 weeks, just worrying about what this interaction looks like. So I'm not going to do that. I'm going to do what physicists always do when faced with this. I'm going to make something up. Completely random, whatever I want. I'm going to make something up that's so easy that we can do this calculation. So I am, however, going to be a little bit careful in what I make up. I'm going to ensure that it doesn't violate any important symmetry properties. So I know some things about the interaction. I know that I want it to have matrix elements between the light and the atom coming in initially, the molecule coming in initially, and the light and the atom going out. So in order to have that matrix element, I need something to annihilate the incoming molecule and something to create the outgoing molecule. Well, I know what does that. An F does one and an F dagger does the other. So for my interaction, I'm going to include an F dagger and an F. Remember, F depends on space and time, and so I am just going to assume, because it makes my life easy, that the F dagger and the F both have a common space-time point. It's a product of those things at the same space-time location. There's no very good reason to assume that right now. Well, I also have my incoming light and my outgoing light, so I need something to annihilate the incoming light and create the outgoing light. That's an E creates and annihilates, so I need two E's or two B's or an E and a B. So I could choose any one of those three. Well, actually, E dot B is what is known as it violates a symmetry known as parity. That is, if I were to look at my scattering in the mirror and I used E dot B, you would get a different answer. I don't like that, so I'm going to not choose E dot B. That's a symmetry argument. If you were to have made the mistake and chosen E dot B, you will get mostly the right answer. So it doesn't matter too much. Now, I'm dealing with a non-relativistic system, and as you're all familiar with, magnetic effects in non-relativistic systems are small compared to electric effects because they go like velocity over the speed of light. So I'm also going to ignore b squared, but again, if I had kept b squared, I would still get exactly the right answer. So I'm just going to keep e squared. Okay, and finally, I'm going to integrate this over all of space, just as I did with what's hidden up there. That's because if there's something that can happen at this point in space, surely it could have happened at this point with equal likelihood. That's translation invariance. There's no preferred spot in my universe. Okay, so there we go. I've got our interaction Hamiltonian. As I said, it was constructed largely out of guesswork, and it may have sounded like it was unique. I said it has to have an F dagger, an E squared. It is by no means unique. In fact, it seems rather unlikely that this one out of the infinite number of things I could have written down should turn out to be the interesting one, but as we'll see, it is. And I will talk about the other possibilities later. Notice that I could multiply this by some number, and indeed I must, because it doesn't have dimensions of energy at the moment. So before we figure out its dimensions of energy, notice that the electric field only couples to charged objects. So inside my nitrogen molecule, there must be charged objects. You know what those are. They're electrons, they're protons. And they have a charge which is set by little e, the charge of the electron, which we know is about 1/3. So for every electric field, I know it's going to come along with an E. There are two of them. That's an E squared. And E squared is this thing we call the fine structure constant alpha. So I'll pull out the fine structure constant. Part of the analysis we perform will allow us to say how the scattering of light by these molecules depends on the fine structure constant. So we'll actually correctly get the charge dependence out of this. I now have to fix up the dimension to make sure I'm actually getting an energy. So first, let's figure out what dimension we have. Well, remember, F had mass dimension 3/2. I have two of those, so that's mass dimension 3. E had mass dimension 2. I have two of those. That's mass dimension 4. 4 plus 3, known to its friends as 7. I have mass dimension 7. But then I integrate d cubed x. For each of these, I get a mass dimension -1. So I get 7 minus 3, which is 4. I'm tired. Which is 4. And I was hoping for an energy. I wanted mass dimension 1. So I have 3 too many mass dimensions. So that means the coefficient here will be some parameter which has dimensions of 1 over mass cubed. Well, 1 over mass cubed is the same as length cubed. So notice that that length cubed has to be some property of the system which is independent of what I'm doing to the light or the molecule. These fields know about whether I'm creating or annihilating molecules with or without momentum and what the wavelength of the light is. So that thing of dimension length cubed can't depend on the motion of the molecule. It cannot depend on the wavelength of the light. What other dimensional parameters are there in this problem, the scattering of light by the molecule? Can you think of anything?
Volume of the system itself.
Say that louder.
Volume of the system itself.
The volume of the system itself. And what do you mean by the volume of the system itself?
The volume in which you have these effects.
Oh, so you're saying I have a totally different interaction Hamiltonian if I do this in a laboratory here than I do in Fermilab where the rooms are all tiny and dark. Probably not. But you're kind of on the right track. It's the volume of something.
Maybe it's the distance between molecules cubed.
Maybe it's the size of the molecule. That's the distance between the atoms, I think is better, because the way we're doing the scattering, by the way, the distance between the molecules is quite large. We're just doing the scattering off of a single molecule. But the size of the molecule could easily enter into this. Well, the size of the molecule is set by the Bohr radius. It's some number, which is a few times the Bohr radius. So I'm going to include a Bohr radius cubed to make up my dimensions. And then there's some unknown constant, which I'll call c. Maybe it's 2 or pi. It's a dimensionless number. At this level of argument, I have no way of figuring out what it is. Okay, but there we go. We've guessed an interaction. Let's at least see what it tells us. Everyone clear at this point? Okay, I said that there would be a lengthy setup, and then the calculation itself is a couple of lines. So we're not quite at the couple of lines, but almost. Okay, so what do we want to calculate? I keep saying scattering of light by the molecule. So what is the measurable quantity that we are interested in? Well, so those of you who have had some undergraduate E&M or quantum mechanics probably knows that when you have scattering, so you have an object, another object comes in, bounces off of that object, the two objects go out. When you do scattering with waves or with quantum mechanics, you have to talk about the probability of seeing the scattered objects come out in certain directions. That probability is given by something known as a differential cross-section. The bread and butter of the measurements here at the LHC, differential cross-sections for various processes. So I am going to tell you very briefly and not in great detail about cross-sections. So the first thing that we can do here is, using the rules of quantum mechanics, is we can calculate a transition probability. That is, I start with my incoming light and my molecule, and I ask, what's the probability that after the collision, the light comes out in some other direction, maybe with some other wavelength, and the molecule comes out with some other momentum? In quantum mechanics, a transition probability is given by the final state that I'm asking about, the interaction sandwiched between the initial state, and quantum mechanics probabilities are proportional to the absolute value squared. Okay, you can do this classically, but it's actually much easier to do it quantum mechanically. But this gives us a transition probability. That's not actually what's measured. What we measure is, well, a rate. We take our molecule and we keep spitting photons at it, electromagnetic waves, and we look in a fixed direction and we see how often the wave comes out in that direction. Okay, that's a rate. We do the experiment for 10 days. We count the number of photons that came out in that direction. We take that number, divide by 10 days. That's the number of photons per day that comes out. That's the rate. That's what we physically measure. The rate for a process, well, if we think about that process, what does it depend on? So I'm the molecule. You are shooting photons at me. I'm batting them away in all possible directions. Of course, if you shoot more photons at me, more photons are going to come out and the rate is going to go up. So the rate is clearly proportional to the number of incoming photons per time. Also, if you're sending those photons spread out over a very wide beam, then fewer of them hit me and what comes out is smaller. So in fact, the right thing to talk about is the flux of photons, which is the number per time per area. And by the way, when you talk about the LHC, when they talk about the luminosity of the LHC, it's the flux of protons. It's the number per unit time per area of the beam that's circulating in the tube. The cross-section is defined simply as the rate divided by the flux. Okay, that's how you define a cross-section. Now, it's called a cross-section because in many simple cases, it is simply the cross-sectional area of the object. So if I'm here, and instead of shooting light at me, you are shooting, oh, let's make it nice for me, ping pong balls, then what happens to the ping pong balls if you look behind me is none of them get through if they hit me, and all of them get through if they go by. So the rate that you get is the flux, the rate at which you're throwing the ping pong balls at me, divided by the area over which they extend, times my area. And those are the ones that get removed from your beam of ping pong balls. So a cross-section, in fact, we can deduce from this, has dimensions of area. Well, area is 1 over length squared. It's -2. And that's really all I'm going to need about the cross-section for now. So the cross-section is the transition probability times a bunch of factors called phase space. Phase space sounds kind of fancy. It's not really. It's just how many different directions could the light have gone into? How many different wavelengths could the light have come out with? So clearly when you ask how many photons came out with a wavelength in this interval in this little angle. Okay, that part of it, the little interval in the angle, is called the phase space. But we're not going to worry about that because we're really interested in the total cross-section. We just want to know what happens to the photons. Do they get scattered at all, in which case they come out in some other direction than the way they were traveling, or do they just go straight ahead? So the cross-section is the transition probability times these phase space factors. But most importantly, I just said that that phase space had to do with the direction the photon was coming out and what its wavelength was. So it's a function. The phase space depends on the properties of the photon. its wavelength, or what have you. But that's all it depends on. Okay, we're now ready for our two-line computation. Let's see if we can figure out what the cross-section is for Rayleigh scattering. So this is what Rayleigh did. Took him more than a year to do it the first time. He did it in some weird theory involving the ether because he didn't know Maxwell's equations. And then 20 years later, he redid it and took him another year to do using Maxwell's equations. Now that we have this background, we'll do it in one line. Well, the transition probability is the square of this matrix element. HI has in it this constant C. So that's going to show up squared. It has the Bohr radius cubed in here. That's going to show up squared. It has an alpha. That's going to show up squared. And what else? Well, it has whatever quantum mechanics says the matrix element of this disgusting operator is in all that phase space. And I'm not even going to bother trying to calculate that because I don't care. I only care about one thing. How does it depend on the wavelength of the light? That I can get by dimensional analysis. Our cross-section is an area. What I have so far is 6 powers of the Bohr radius. Well, that's an area times 4 powers of the Bohr radius. So to make this dimensionally right, I got to get rid of those 4 powers of the Bohr radius. And the only parameter I have is the wavelength of light. There you go. That's what Rayleigh struggled to get. I told you it would be 3 lines. Yeah, after 30 minutes of conversation, it's 3 lines. Now, there is some factor in front which I do not know. But I didn't know what this number C was anyway, so it's sort of a waste of time to worry about those factors very much. You can compute them. It's not hard. If you know quantum mechanics, it's a matter of 10 minutes or so to compute those factors. So if you knew C, you could actually compare and see that you get exactly Raleigh's answer. Okay, so what does this have to do with why the sky is blue? Well, that's the classic example. So when you look at the sky, what do? You look like that. But where's the light coming from? The sun. It's coming this way. So the light that you see isn't coming directly from the sun. You know, your mother told you never look at the sun. The light has to be scattered by those molecules and come down. If it's not scattered, you don't see it. But the scattering depends on the wavelength of the light. The shorter the wavelength, the bigger the scattering, the more likely the light was scattered. So the long wavelengths don't get scattered much. They go this way and you don't see them. The short wavelengths get scattered much more and you see those. So the color of the light is shifted towards the blue end of the spectrum. That's why the sky is blue. Okay, Raleigh's explanation. So it was all about this lambda to the 4th, which we got after a lot of words, as I said, with pretty much no effort. Okay, are you amazed? Probably not. So there are a couple of comments about this, which is why I did this example. The first comment is to get the lambda to the 4th, all I had to know was the dimension of the operators that appeared in the interaction. That's what said there had to be a length cubed. We had some discussion and decided that that length should be the Bohr radius. But even if I were wrong and it's not the Bohr radius, it's some other length, I still would have gotten 1 over lambda to the 4th. The only thing I really needed to know was that the wavelength lambda is much bigger than that length scale. Because if that's not true, then I'm not doing this averaging and I have to know what's inside the molecule in that. So the only requirement, this is true provided lambda is large compared to that. It doesn't actually have to be the Bohr radius, but it is indeed the Bohr radius. Okay, now more importantly, I made this interaction up. So I got Raleigh's answer, and you might reasonably say that I have cheated you. I knew what the answer was, and so I picked the operator that was going to give me this answer. I assure you that is not what I did. Let me now argue that this is, in fact, inevitable. Well, first, let me show you a different operator that we could have chosen that also leads to scattering of our long wavelength light by the molecule. I could have taken an interaction which looks like that. It's not quite the same interaction I had before. It has two additional derivatives of the field F. Nothing wrong with that. It still annihilates the incoming molecule, creates the outgoing one, annihilates the incoming photon, creates the outgoing photon, has all the right symmetries. It's a perfectly reasonable guess for the interaction. So I didn't include it. Maybe I should have used this one, or maybe I should have both. Is there any reason why we would ignore this one? Well, let's go through our analysis again using this one. So what was the first thing we tried to do? This was supposed to be a contribution to the interaction Hamiltonian. It must have dimensions of energy, so we figured out what its coefficient was. Well, this coefficient is the same as what I had before, which was a cubed. But now I have two additional derivatives. The two additional derivatives are an extra length in the denominator, each one. So 2 extra lengths in the denominator, I have to compensate for that. So that's another a squared. That is, this interaction has a coefficient not of a cubed, the Bohr radius cubed, but the Bohr radius to the 5th power. So what would have happened to my cross-section? Well, let's say I have both of these operators. So this one, I still have an alpha, I have a C2, and I include it. So I then would have to add to this what I get from this operator. Well, I now have a to the 5th, and I square it, so that's a C2 squared a to the 10th alpha squared, and now what do we have down here? Lambda to the 8th. So that looks very different. It's not Raleigh's answer. Is it wrong? Why is it negligible? Well, A has units, so it's hard to, if I choose a unit where the Bohr radius is 1 glotz, then it's still 1 glotz to the 10th power. So you're on the right track, but how do you know when something is small? How do you decide if something is small or not? You have to compare it with an appropriate length scale. Notice that this term is the same as this term by a factor that's of order a over lambda to the 4th. But this is very, very tiny by assumption. We have a long wavelength light scattering off of a tiny object. So we could have included this operator. Indeed, we probably should have included it. That is, in nature, that's probably there. But it makes a totally negligible contribution to the process. Okay, was that clear? That's the key to everything. Because this parameter is so small, the contribution of this operator is completely negligible. If we were trying to do incredibly precise measurements of this scattering, where, remember, lambda is 10 to the minus 7, a is 10 to the minus 10, this is 1 part in 10 to the 12th. If we were capable of measuring the scattering of light by a nitrogen molecule to 1 part in 10 to the 12th, which I assure you we are not, we would be sensitive to the existence or non-existence of this interaction. I assure you we would see it, we'd measure it, and we'd be very happy. But clearly, if we're not interested in an accuracy of parts in 10 to the 12th, we do not need to include this. Okay, you ready for the general argument? So I wrote down an operator which I said I just made up. Well, that was a white lie. I didn't just make it up. I knew it was going to be the most important of all possible operators, in the sense that we discovered here. That is, every other operator we can include in our interaction, I will now prove for you, gives a smaller contribution than the one we included by powers of A over lambda. You get the idea? The proof is insanely simple. It's just counting. In constructing an operator for our Hamiltonian, we have four things, well, we have only a few items we can use. We have electric or magnetic fields. We have F and F dagger, and we have derivatives. That's all we got. So notice that every additional F or F dagger, well, they have to come in pairs because we always have to include pairs of molecules, but every F or F dagger increases the mass dimension of the operator by 3, which means it's going to increase the coefficient by 3 more powers of A, and consequently we're going to get more powers of A upstairs compared to what we got here. So more F's clearly are no good. They are irrelevant to this calculation. E has dimension 2. Any more powers of E always come with at least 2 more powers of A. Once again, irrelevant. And derivatives? Well, derivatives have a length downstairs, so you have to cancel that with more powers of A upstairs. And once again, any extra derivatives give you irrelevant terms. And that's the argument. So what I did in my head in constructing this is I knew I wanted the fewest number of fields possible. So that's the minimum. If I have fewer than that, I don't annihilate or create the particles I want. And I want the fewest number of derivatives, 0 in this case. Now, the real interaction between my molecule and light is complicated because it depends on the detailed structure of that molecule. And presumably, all the operators I can write down are present. It's not that they aren't part of the interaction. They're there. It's just their matrix elements are so tiny, I don't need to worry about them. Okay, this trick that you can take the real interaction without even knowing the details of what's going on and divide it up into operators with different dimensions, then the operator with the smallest dimension is the most important one. That's the trick. This trick goes by a name. It's called effective field theory. Effective because we've actually replaced the real theory that we think describes the system. What's the real theory that describes the system? Well, it's at least the standard model. I did not try to compute this using the standard model, just as you in your coursework have not started with the standard model and then deduced what happens when bowling balls collide. That's presumably the real field theory that describes this system, but I used a different one. A much simpler theory that I knew was guaranteed to give me the right answer. That's called an effective field theory. An approximation to the real one that is vastly simpler, and the approximation is controlled in the sense that you can make the approximation as accurate as you need to. So just as I discussed here, if I measured that light scattering off of the molecule to parts in 10 to the 12th, I'd have to include those other operators. But I'm capable of doing that. So if the experiments are that precise, I got to include them. Okay. In fact, this procedure of how to replace one field theory with an effective one systematically and in a controlled way was worked out over many years by many people, but finally understood and packaged in an appropriate way by Ken Wilson in a framework now called the renormalization group, for which he received the Nobel Prize about 15 years ago. And so secretly, that's where these lectures have been headed, to teach you the Nobel Prize-winning work of Ken Wilson, which is the underpinnings of the laboratory like this one. So we've seen it in one example. What we will do next time is we will actually describe the more general procedure due to Wilson, and then we'll apply it to everything under the sun. And I mean that literally. Okay, thank you.